Okay, so now where are we, Rachel?
Yeah, at glycine.
Okay, glycine. So Sarah already got us there. So glycine was just the side chain. Methylene is going away from serine. The water we never care about.
And then you can make glycine
from scratch. Yeah, I don't know where that came from. It was in the slides.
And then cysteine.
Oh, now we're at cysteine?
Yeah.
Okay. Right. So cysteine, we start with serine, don't we? Yeah. Because we can see because oxygen and sulfur are chemically similar. So we just need to convert that side chain hydroxyl to a sulfhydryl. That's all well and good, but where do we get the sulfur atom? Methionine. So that's why we need. So we can make that if we have methionine. So and I don't know. There was some comment there about it's PLP, two enzymes, both PLP dependent. I mean that's kind of a bit complicated, but it's some funny chemistry. So it takes some special coenzymes. So that's how you get there, because it's not readily apparent when you look at it the way much of this other chemistry is. Okay, now are we getting close?
Yes.
Tyrosine. Okay, so tyrosine we have to have phenylalanine, isn't it?
Yes.
And it's just an oxidation. Is it? What does it involve, Jonathan? How do you make tyrosine? Sorry.
Phenylalanine, yeah, or
Okay.
phosphatidylpyridine.
Oh, so that other one is for, that's the essential pathway.
Can you explain that again?
Well, it's just that the slide is kind of misleading because, what is it, the bold ones are the ones that are non-essential that we can make, isn't it? The bold ones are essential? And then I underlined or something too, isn't it? Anyway, you can get to, as Jonathan pointed out, you can get to tyrosine via, is it pentose phosphate pathway in glycolysis?
Yes.
Okay. But we can't do that. We don't have those enzymes. So there must be multiple steps. We lost those enzymes. So that's for plants and bacteria and other stuff. So the only way we can get there is from phenylalanine. Yeah. Is that an oxidase, or what is the name of that thing? There's no name? Yeah, I mean it's got to be something exotic, an oxidase to put that hydroxyl on. But okay, right. I mean we know we can't just insert a hydroxyl into carbon-carbon bonds. If we have a hydroxyl there, it's simple. But just to put one in de novo is tricky. So now are we done?
Small molecules, yes.
But with the amino acids?
Oh, yes.
Okay.
So we need to know about the small molecules.
Okay, but just for the amino acids, can you see that wasn't really tough sledding or anything, was it? You can see why some of them are important and some of them are pretty apparent, and just got to kind of wonder, where's the sulfur come from, or so I think that takes a pretty tedious portion of the course content and just streamlines it. Okay, so now we're just talking about making stuff. Yeah, so that we actually touch on in various lectures, some of these. I think the ones that are underlined or highlighted or something. So just bear in mind that many small molecules come from amino acids, so that's why we need to make them, in addition to having them charged on tRNAs for translation, for polypeptide synthesis. So, okay, and then we're into heme biosynthesis. So this guy, this crazy Canadian scientist that ate the labeled precursors, what was the gist of his finding? He through these tests that he performed on himself, taking his blood, he found that heme is synthesized through the condensation of two types or two molecules. One's an amino acid, which is glycine, and the other, you know, the label was in acetic acid, but it turned up into something that's part of the TCA cycle, which is succinyl-CoA. So those two condense, and then you're off on your merry way. I guess it makes delta aminolevulinate or something, and then you condense those, and I don't know, do you condense again? You asked me about that, didn't you, sir? Like the number?
Yeah,
it wasn't straightforward.
Yeah.
Okay?
Yeah.
So, yeah. So anyway, it's a bunch of condensations that originate from a TCA cycle intermediate and the simplest amino acid. So that amino acid is where you're going to get the nitrogen groups in the heme. The disease is at the end. The disorder is kind of interesting, kind of strange. Yeah. Okay, so now where are we, Kim? Oh, integration of metabolism. Yes. I'm not, except with the exception of the gout in this Lesch-9 that's related to purine biosynthesis. Okay, I feel like those are kind of more biomedically relevant.
So we don't need to know the heme at all? So we don't need to know heme at all? These in?
Yeah, what was the second one?
Lesch-9.
What about the disease from the free amino groups?
Purine. It's at the end of the purine biosynthesis.
The free amino
What's the
disease,
free amino?
where it causes like brain swelling or something?
Well, it's just you know, we touch on ammonium being toxic, so why? It's just interesting to know why, I think. Okay, integration of metabolism. The first chunk of it's pretty fluffy, pretty general, superficial. We've seen these concepts just to kind of bring them up again. Then we get into the different pathways. And these key regulatory steps that we focused on before. And there's a few pathways with additional regulatory steps that we hadn't touched on, that it wouldn't hurt you to be familiar with those too. I think the new ones were the acylcarnitine transferase. So it's regulation of fate oxidation. And then there was one regulation of fatty acid biosynthesis where you had feedback inhibition from palmitate. And see, I'm kind of jumping into the middle of these. It's too bad, you know, on these handouts there's no color. So you can see the red inhibitors and the green activators. Might want to go back and look at those PowerPoints, the color. So then, but we looked at these different pathways. We looked at, there's pentose phosphate pathway. So first step, committed step, and is it regulated covalently? Is it regulated allosterically, or other? None of the above. D. That was C. None of the above, right? Because how does it work? How do we regulate our pentose phosphate? NAD, P plus, which is the what? Is that the product or the? It's the substrate. So this is the simplest of simple regulatory mechanisms. It's just substrate availability, period. So where's that happening? In the allosteric side or the active side? Active side. There is no allosteric side. So it's not allosteric, it's not covalent modification with a kinase phosphatase cycle. It's just, is there NADP plus, period. Okay, so I think the remaining two